Given a sorted array of integers, the objective is to locate the exact index of a specific target value. If the target doesn't exist in the array, the system returns -1. Mechanically, this mirrors looking up a word in a physical dictionary. You open to the middle, check the letter, and discard the half of the book that cannot possibly contain your target. This chart visualizes the efficiency difference. A standard linear scan evaluates the array block by block, resulting in an O of n time complexity. Binary search repeatedly slices the search space in half. By discarding half the remaining options at every step, the algorithm rapidly shrinks the search range. This continuous halving shifts the time complexity from linear to logarithmic, or O of log n. Conceptually, dividing a space in half is intuitive, but translating that halving mechanism into a robust code introduces severe engineering friction. Implementations frequently fail. The logic requires absolute precision regarding index tracking, making it highly susceptible to errors that lock the system into an infinite loop. These failures typically occur when developers rely on rote memorization of code snippets rather than grasping the strict mathematical rules governing the pointers. Deducing the loop invariance and boundary conditions from first principles ensures the resulting code accounts for edge cases that usually trigger errors. To deduce these rules, we start with a clean, continuous sorted array. This diagram illustrates our active search space. We define initial boundaries by placing a left pointer at the 0 index and a right pointer at the final index. To make our first halving decision, we calculate the exact midpoint. With an even number of elements, convention dictates selecting the first of the two middle elements. This is equivalent to performing integer division on their sum. To make our first halving decision, we calculate the exact midpoint. With an even number of elements, convention dictates selecting the first of the two middle elements. This is equivalent to performing integer division on their sum. Calculating this sum exposes a critical vulnerability in memory management, the integer overflow trap. This comparison shows the mechanics of overflow. In strongly typed languages, adding large left and right pointers directly can exceed the maximum limit for integer storage. To remain memory safe, developers must use the formula left plus the floor of right minus left divided by 2. This universal constraint, however, doesn't apply everywhere. Because Python allocates memory dynamically for arbitrary precision integers, the standard formula of left plus right, floor divided by 2, calculates the midpoint safely. The method for finding the middle of an array changes depending on the language's memory architecture. The algorithmic logic is tightly bound to the specific compute mechanics of the environment. With the midpoint safely calculated, we can execute the core binary decision. This diagram compares our calculated midpoint against the target value of 5. The inequality shows the midpoint is strictly less than the target. Because the array is sorted, every integer to the left of the midpoint is guaranteed to be smaller as well. We aggressively discard this entire section of the search space, including the midpoint element itself, as we proved it doesn't equal the target. In code, the left pointer snaps to the index immediately right of the old midpoint. Updating the boundary to exactly mid plus 1, or mid minus 1 for the right boundary, is non-negotiable.
If a developer sets the new boundary exactly at mid, they trap a proven false value inside the active search space. It becomes dead weight. That dead weight prevents the pointers from crossing. The algorithm becomes trapped, evaluating the same useless elements in an endless loop until the program crashes. Strictly excluding evaluated elements is the mechanical engine that drives the algorithm forward. It guarantees the space physically shrinks with every step, enforcing logarithmic progression. The ultimate stress test for this boundary logic is a search space containing only a single element. This diagram displays an array constrained to a single index. The left, right, and midpoint variables physically collapse onto position 0. If the core while loop condition is left is strictly less than right, the logic breaks down immediately. Since position 0 is not strictly less than position 0, the loop terminates without evaluating the element, entirely missing the target. To survive this edge case and evaluate the final element, the while loop condition must include equality. Left is less than or equal to right. With the loop logic secured, the final architectural consideration is memory efficiency. Binary search can be written recursively, calling a new instance of the function for each halving step, rather than using an iterative while loop.
This split screen contrasts execution cost. Recursion incurs a structural penalty, building a growing vertical stack of memory frames proportional to the number of steps, yielding O of log n memory complexity. The iterative approach updates pointer variables in place, requiring only a single constant block of memory, maintaining a strict O of 1 footprint. Accounting for single-element edge cases and minimizing the stack memory footprint allows the algorithm to function reliably within tight system constraints. We now have a mathematically sound, fully deduced architecture. Looking at the completed pipeline code, we see the specific termination constraint we deduced. The equality ensures survival in single-element arrays. The midpoint calculation utilizes Python's floor division operator, safe from integer overflow due to dynamic memory allocation. And the boundary updates correctly apply the plus and minus offsets, aggressively excluding evaluated elements to eliminate the risk of infinite loops. While this logic is designed to navigate sorted arrays, the halving concept scales well beyond hunting for integers. These exact mechanics can be deployed in any scenario where a single binary decision reliably eliminates half of the remaining options. It is used to isolate the specific commit that introduced a bug in a massive software deployment, or to pinpoint the maximum capacity limit of a distributed network. A vastly complex operational space rapidly condenses through binary elimination, locking onto a single state in a fraction of the time linear evaluation requires. This halving principle provides a foundational pattern for advanced system design, allowing engineers to navigate massive datasets and complex configurations. Deducing algorithms from first principles strips away reliance on memorization. It forces an understanding of the mechanical constraints, yielding resilient problem-solving models that engineers can trust in production.